Thank you very much. Thank you for your kind introduction. And today, indeed, I want to tell you how we can use this long cycle to, in the end, work towards single molecule resolution by sensing in urine. So our ultimate goal is to perform early cancer diagnosis. And to do so, we want to detect tumor DNA in urine because it's a low invasive technique, and that's of course good for the patient. But how would that be possible? Well, all your cells now and then excrete part of their genome, just like tumor cells. And they excrete this genome via extracellular vesicles or via cell. And this means that in the end, this DNA can end up in the bloodstream. And there it starts circulating. And at one point, it will actually end up in the filters of the body. A small DNA fragments can actually pass the filters of the body and this way in urine. So this is how we actually will be able to detect tumor DNA, among other DNA. But you can imagine, we want to perform early cancer diagnosis. And in the early stage of cancer, tumor is just small, and having to find, tumor DNA is like having to find a needle in a haystack. So how to approach this issue? Well, I think the best way to actually approach this is making small portions of the enormous haystack and start looking for that one needle. And this is actually what we do by the use of digital sensing. So let's get digital. So most sensors nowadays are still based on bulk or analog sensing, where the amount of signal is directly equated to the amount of molecules. But ultra low concentrations generally also means ultra low signal. So therefore, people came up with single molecule sensing, where they actually either decrease the sensor area or the total volume of sensing, and in that way they can look at single molecules. However, if you want a good representation of your entire sample, you have to repeat this many times. It makes it very unintuitive. Therefore, the best of both worlds is finding physical single molecule sensing, where you actually have a lot of these single molecule sensors in parallel, and you just count the amount of events and find statistics you can relate this back to the original concentration. So the single molecule sensor we are working on is this one, which consists of a gold nanoparticle, a DNA-Origami. This example is a very simple one, just a hairpin, and a gold cell. And upon addition of targets, the hairpin will actually change its conformation. So you can actually see that the hairpin will unzip, and then we will end up with what we call an extended state. And we want to sense this, and how are we actually going to sense this? By using the unique properties of gold nanoparticles on top of gold cells. Because the gold nanoparticle on top of a gold film will see its mirror image and will start actually interacting with it, which causes a change in the electromagnetic coupling. And the nice thing is that this also changes the scattering property. So you can see the closer the particle is to a gold film, the more red shifted the scattering color will be. Well, if we go further and further away, we will see a blue shift and end up with green particle. So this is actually how we want to look at it. We want to determine the height of the gold nanoparticle by looking at the red over green ratio. And of course, we want to do digital, so we will have a gold film with lots of these single molecule sensors. Then, if one small target comes in, it will bind to one of these sensors, and we will see a green shift, as is shown over here. So this is the ultimate goal. But I hope you appreciate that the most important part of the sensor is, of course, the hairpin, because this one determines whether we can see the change in conformation. So therefore, we first start with checking whether we at least can see that the hairpin is open in the presence of targets. And here we perform gel electrophoresis, and for everybody who's not familiar with it, we actually load DNA here, and we apply a potential, and then all negatively charged DNA will move towards the positive pole. But because the molecules can be bulky or less bulky, they will travel with a different speed. And over here you can see that the target complex actually travels less far, which is of course expected because it's bigger than the hairpin itself. So this already suggests that the hairpin is opening, but we wanted more proof. So we also looked at crystal resonance energy transfer, where we have a hairpin on each side of the hairpin, so on the 3' and 5' ends, we will label it fluorophore. And one fluorophore will act as the donor, and the other one as the acceptor, which actually means that if they're in close proximity and we excite the donor, we will see the emission of the acceptor. But when there is an increased distance, this is not possible anymore. And we can nicely see that if we add more and more targets, we see a restoration of the emission of the color, which means that we get come to this state. So here it is. But now, of course, we want to use this for single molecule sensing. Therefore, we have to ensemble the sensor. And this is a schematic of the sensor, which consists of the gold film, and a tether layer, which is an undecaan layer with on top of polyethylene glycol to make sure that no biofouling can happen, because you can imagine in urine there's multiple things we don't want to sense. Then we can immobilize the DNA on top, and of course, the gold now. Of course, we also want to check examining the sensor, so we perform quartz crystal microbalance measurements, where every binding of a molecule can be seen as a dip in the frequency, just by string theory. And what you can see is that we over here have the monolayer, but some molecules in the self-assembled monolayer actually have a carboxyl group. And we can activate this carboxyl group to bind the amine group of this hairpin. And we can actually very nicely see that we see a dip in frequency, so we actually bind this hairpin. Then, of course, we want to activate nanoparticles, and we see it usually because they're pretty heavy. And then we want to make sure that no molecules can bind nanoparticles, so we activate. Then we add non-target DNA, so we almost see no dip. And when we add target DNA, we see a huge dip. So it already shows that this assay is working in bulk, but we want to perform single molecule measurements. So then the main question is, if we are actually only looking at the differences in Z height, what is the difference in Z height between the hairpin state and the extended? And to find out, we performed numerical simulations. So we developed an in-house method that actually is based on a worldwide chain model, where we built a chain depending on the properties of our DNA chain, and then add the particle on top. And if we repeat this over and over and over, we will end up with a probability map. Because some states are just not possible because the particle clashes with the chain or with the surface, and we discard these. And then we end up with a probability map, which is just the likelihood of the particle to be at a certain position over time. And we can actually use this to reveal the Z height distributions. You can see that there is a quite distinct Z height distribution between the extended state and the hairpin state. And if we then look at the average, you can see that indeed the average Z height is. So this is good, but this is not what we're observing, because what we actually observe is the change in color. So we added another set of simulations, which was done by the nanoparticle bounding element toolbox, which is a free toolbox you can just download on the internet. That's always nice. And if we couple the information on the nanoparticle towards the data we have over here, we can actually predict the spectra of this. They're quite distinct, but unfortunately, since we want to look at the red-mean ratio, we only look at this part, because this is the visible part the camera can see. And if we then also add the sensitivity of the camera towards the different colors, we can predict the red over green ratio. The camera should be able to see. And we see that there is a difference, but it's not super big. And then, of course, we want to prove real measurements. So here you can see dark field measurements before the addition of target and after the addition of target. And unfortunately, you see it. But we also plotted it here. And you can see that the red over green before the addition of target, red shift, which is expected. And at the moment you add targets, you see a green shift. However, the shift is much larger than we saw in simulations. So in the future, we really need to find out whether this is the truth or we just forget stuff in simulations. But at least we can show that this assay is working pretty well. So to conclude, we confirmed the opening of the DNA hairpin. We confirmed the sensing principle by the scan plots I showed you. And we numerically predicted the assay outcome, which did not fully match. And we also showed that we approved the principle with the optical. So of course, we want to go to the end products, but then we first need to understand the differences between the simulations and measurements so we can better actually design our assay. Furthermore, we need to determine the limit of detection because the previous measurements were at 1 micromolar. That's a really high concentration. And in the end, we need to go to femtomolar, maybe even attomolar concentrations. And then, of course, in the end, we want to measure directly or after pre-treatment in urine sample. make sure that we can perform cancer diagnosis. And in the end, we of course also want to multiplex, because the more DNA samples you can measure simultaneously, the better you can predict whether a patient has cancer. And we actually already published a paper about this last year, where we performed a lot of simulations to show whether this was possible or not, performing multiplex measurements. And this multiplexing is solely based on changing the stem of the hairpin. And how does it work? Well, the longer the stem is, the larger accessible volume of the gold nanoparticle. And it has also more degrees of motion, because the stem in the end will be single-stranded, which is of course far more flexible than the double-stranded. So if we then look over here, you can see what happens if we would look at average position, like we do in our current research. Then there's not a lot of difference. But if you start looking at the dynamics, so really the moving of the particle, so the change in the resonance ratio over time, you can perfectly look at the differences of only 10 nucleotides. So we hope that in the future, we can also show this in experiments. Then of course, I didn't do this work all by myself. I work in the bias lab at the University